variation of thermal efficiency versus pressure ratio could be given as y-axis is ideal Joule cycle thermal efficiency versus pressure ratio RP. For a fixed T max by T minimum ratio, where T max is the peak temperature and T minimum is the ambient temperature, could be given in this manner. And the variation of the work ratio with RP could be seen as, incidentally, the pressure ratio at which work ratio is maximum is given by RP opt, where thermal efficiency is maximum when RP is equal to RP max. RP opt is a square root of RP max. Most of the times our criteria is to get maximum work output, hence usually the pressure ratios commonly in gas turbine power plants which run on Joule cycle or Brayton cycle are kept in the range of 6 to 10. For such pressure ratios, the compressor suitable is centrifugal type of compressor or a multi-stage axial flow compressor. The Joule cycle with machine efficiencies is given in this following manner. On the TS plane, taking into account the losses that occur in the compressor and the turbine could be given in this manner. One two two dash is isentropic compression of air, where 122 is actual compression, that is adiabatic compression only with the friction. In the figure 324 dash is isentropic expansion or reversible adiabatic expansion of gases in the turbine, whereas 324 is actual expansion of gases with friction. In this context, we can define isentropic efficiency of compressor is defined as isentropic work input to compressor divided by actual work input, which could be given mathematically as Cp of air into T2 dash minus T1 divided by Cp of air into T2 minus T1. It results in T2 dash minus T1 divided by T2 minus T1. Usually, isentropic efficiency of the compressor is in the range of 85 to 90%. Similarly, for turbine, isentropic efficiency is defined as actual work output of turbine divided by isentropic work output, that is frictionless adiabatic work output is isentropic work output. Usually isentropic efficiency of the turbine is in the range of 90 to 95%. With the machine efficiencies taken into account, the actual thermal efficiency of the Joule cycle would be slightly lesser than the ideal Joule cycle thermal efficiency. Now let us consider a problem on gas turbine power plant given in GATE 1998. Problem on gas turbines. The problem is given like this. Find the required air-fuel ratio in a gas turbine whose turbine and compressor efficiencies are 85% and 80% respectively. Maximum cycle temperature is 875 degrees centigrade. The working fluid can be taken as air. Cp is equal to 1 kilojoule per kg Kelvin. Gamma is equal to 1.4 for air, which enters the compressor at 1 atmosphere and 27 degrees centigrade. The pressure ratio PR is 4. Fuel has a calorific value of 42,000 kilojoule per kg. There is loss of 10% calorific value of fuel in the combustion chamber. The solution to this gate problem could be given like this. Let us indicate the cycle, Joule cycle for the gas turbines on the TS plane. The cycle is with machine efficiencies. Therefore, 1 to 2 dash is isentropic compression, 1 to 2 is actual compression, 3 to 4 dash is isentropic compression. 3 to 4 dash is isentropic compression, 3 to 4 is actual compression. 3 to 4 is actual, the side going curve, actual expansion. 3 to 4 dash is isentropic expansion. 1 to 2 dash is isentropic compression. 1 to 2 is actual compression with friction. First of all, let us calculate T2 dash from the given data. He has given T1 as 27. When it is converted into the Kelvin, it becomes 300 K. Pressure ratio is given as 4, that is P2 dash by P1. Let us write the isentropic relation between 1 to 2 dash, that is P2 dash by P1 is equal to whole power gamma minus 1 by gamma is T2 dash by T1. T2 dash is equal to 300 into Rp to the power of gamma minus 1 by gamma, that is equal to 300 into 4 to the power of 0.4 divided by 1.4, from which we will obtain the T2 dash temperature in Kelvin scale. By using isentropic efficiency of compressor, which is defined as T2 dash minus 1 divided by T2 minus T1, which is given as 0.80 in the problem, we can calculate the actual temperature of the air leaving the compressor in Kelvin, because T2 dash is already calculated and T1 is 300 Kelvin. We can easily obtain the temperature of air leaving the compressor, that is T2. T2 is temperature of air leaving a compressor. We can easily fill the blank for T2. Now, considering the Tmax, that is T3, which is given as 875, when converted into Kelvin, we have to add the 273. 3 to 4 dash is isentropic relation. Therefore, we can use the isentropic relation, that is T3 by T4 dash is equal to P3 by P4 dash whole power gamma minus 1 by gamma, that is equal to Rp to the power of gamma minus 1 by gamma. Now, substituting the values for T3, that is 875 plus 273 divided by T4 dash is equal to 4 to the power of 0.4 divided by 1.4, from which the T4 dash could be calculated. From the definition of isentropic efficiency of turbine, T3 minus T4 is equal to T3 minus T4 dash, that is equal to 0.85 is equal to 875 plus 273 minus T4 divided by T4 is already obtained above. This T4 dash could be substituted here, and the actual value, actual temperature of gases leaving the turbine could be calculated, from which thermal efficiency of gas turbine cycle could be obtained as work of turbine minus work of compressor divided by heat supplied in a combustion chamber, that is Cp of the air into T3 minus T4 minus Cp of the air into T2 minus T1 divided by Cp of the air into T3 minus T2. The thermal efficiency could be easily obtained for the actual gas turbine cycle, taking into account the machine efficiencies or losses that occur in the compressor and the turbine. Now, writing the first law of thermodynamics or law of conservation to combustion chamber as, let mf be the mass of the fuel consumed in the combustion chamber. Therefore, how much heat will be liberated? mf into calorific value into efficiency of the combustion, because there are 10% losses are there in the combustion chamber. Here efficiency of combustion would be 90%. This is the heat liberated in a combustion chamber, that is equal to mass flow rate of air used for combustion of the fuel plus mass flow rate of the fuel, that is total mass flow rate of the gases generated. Ma plus mf shall give the total mass of the gases generated into Cp of the air, because the gases are assumed as same as that of the air, having the same specific heat as that of the air. Cp of the gases and Cp of the air can be taken as the same, into T3 minus T2. This is the law of conservation of energy or heat balance equation for the combustion chamber. Left hand side of this equation indicates the heat liberated in the combustion chamber due to the combustion of the fuel, whereas right hand side indicates the increase in enthalpy of the gases, that is mass of the gases into specific heat of the gases, which is taken as the same as that of the air, into temperature rise of the gases in the combustion chamber, that is from state 2 to state 3. Dividing both sides with the mf, mass of the fuel consumed, we get calorific value of the fuel into efficiency of the combustion is equal to ma by mf plus 1 into Cp of the air into T3 minus T2, where ma by mf is the air-fuel ratio used in combustion chamber of gas turbine cycle. because everything else is known in this equation, that is CV of the fuel is given as 42,000 kilojoule per kg into efficiency of the combustion in this case is 0.9, MA by MF is unknown, CP of the air is, it can be taken as 1.005, and both the temperatures, that is T peak, T maximum temperature or T3 is already given in the problem. We had calculated TT previously, T2, the temperature of the air at the entry to the combustion chamber or the temperature of the air leaving the compressor is calculated earlier. Therefore, air fuel ratio MA by MF could be easily calculated. Normally, the air fuel ratios employed in the gas turbine power plants vary in the range of 50 to 60. It may go up to 70 or 80 sometimes. Usually you will be getting 60 kg of air will be used to burn 1 kg of fuel in the combustion chamber. Now let us do another problem on gas turbine cycles, which was given in GATE 2000 problem on gas turbines. The problem is given like this. In an ideal air standard gas turbine cycle, the minimum and maximum temperatures are respectively 310 K and 1100 Kelvin. Draw the cycle on a TS diagram and calculate optimal pressure ratio of the cycle for maximum work output. Assume for air gamma minus 1 by gamma, where gamma is Cp by Cv or ratio of specific heats for air as 1.4. Now the solution to this problem could be given like this. First of all, let us indicate ideal Joule cycle or ideal Brayton cycle on temperature entropy diagram. One, two, three, 4. 1 to 2 is isentropic compression. 2 to 3 is constant pressure heat supply in the combustion chamber. 3 to 4 is expansion of the gases, where the gases does work on the turbine, and 4 to 1 is the constant pressure heat rejection. The RP optimal, that is a pressure ratio for maximum work output, is given as T max by T minimum divided to the power of gamma by gamma minus 1 into 2. That is, here the T max is given as 1100 Kelvin, T1 or T minimum is given as 310 Kelvin. Therefore, RP opt is that is the pressure ratio required for maximum work output is 1100 divided by 310 to the power of 1.4 divided by 2 into 0.4. This is the answer for problem, or this is the answer for our optimum pressure ratio. Now let's do a problem on gas turbines given in GATE 2003. Gas turbine problem. The problem is given like this. In a gas turbine, hot combustion products with the specific heats Cp is equal to 0.98 kilojoule per kg Kelvin and Cv is equal to 0.7538 kilojoule per kg Kelvin. Enter the turbine at 20 bar, 1500 K and exit at 1 bar. The isentropic efficiency of the turbine is 0.94. Then the work developed by the turbine per kg of gas flow is A 689.64 kilojoule per kg, B 799.4.66 kilojoule per kg, C 1009.7 kilojoule per kg, D 1312 kilojoule per kg. The solution to this problem could be obtained by considering the expansion of the gases on the temperature entropy diagram. 1 to 2 dash is isentropic expansion of the gases because it is a vertical straight line or reversible adiabatic expansion of the gases in the turbine. The actual expansion is 1 to 2. 1 to 2 is actual expansion, adiabatic only, but with friction. 1 to 2 dash is isentropic expansion. Therefore, isentropic efficiency of the turbine is actual work output, that is Cp of air into T1 minus T2. Any work output in a gas turbine is nothing but Cp into delta T. That is, numerator is actual work output divided by Cp of the air into T1 minus T2 dash. This is the isentropic work. But we do not know the 2 dash, T2 dash. We were given in the problem T1 as 1500 Kelvin. We are given P1, pressure P1 as 20 bar and P2 as 1 bar. We know the pressure ratio across the turbine, that is 20 by 1, which is equal to the 20. I use the isentropic relation between 1 and 2 dash. T1 by T2 dash, T1 by T2 dash is equal to P1 by P2 dash whole power gamma minus 1 by gamma, which is equal to 20 by 1 to the power of 1.4 minus 1 divided by 1.4, from which T2 dash could be obtained as 1500 divided by 20 to the power of 0.4 divided by 1.4. We can obtain T2 dash. Because isentropic efficiency of the turbine is given as 0.94, T1 that is equal to T1 minus T2, which we do not know, divided by 1500 minus T2 dash, which is calculated here. From this equation we can calculate T2. Then actual work output is equal to Cp of the air into T1 minus T2. This is equal to 0.98, Cp of the gases, 0.98 into 1500 minus T2, which is already calculated earlier. The answer would be 689.64 kilojoule per kg Kelvin. 689.64 kilojoule per kg amount of work is done actually by the turbine. Now let us do another problem given in GATE 2001 on gas turbine power plants. The problem is given like this: a Brayton cycle, that is air standard, which means working fluid is taken as air, has a pressure ratio of 4 and inlet conditions of 1 standard atmospheric pressure and 27 degrees Celsius. Find the airflow rate required for 100 kilowatts power output if the maximum temperature in the cycle is 1000 degrees centigrade. Take gamma of air as 1.4 and Cp of air as 1 kilojoule per kg Kelvin. The solution to this problem is given like this. Now let us draw the Brayton cycle, ideal Brayton cycle on TS plane. One, two, three, four. He has given T1 as 27 plus 273 Kelvin, that is 300 Kelvin. P2 by P1 is equal to pressure ratio Rp is given as 4. And P1 is also given as 1 standard atmospheric pressure. Let us consider it as 101.3 kilopascal. That is the standard atmospheric pressure value. Now let us calculate what is T2. T2 by T1 is equal to P2 by P1 whole power gamma minus 1 by gamma, that is equal to Rp to the power of gamma minus 1 by gamma, that is 4 to the power of 0.4 divided by 1.4, from which the temperature of the air leaving the compressor is obtained as T1, that is 300 into 4 to the power of 0.4 divided by 1.4. From this, the temperature of the air leaving the compressor can be obtained in Kelvin. The maximum temperature, that is T3, is given as 1000 centigrade, that is 1000 plus 273 Kelvin. Using the isentropic relation between T3 and T4, that is T3 by T4 is equal to P3 by P4 whole power gamma minus 1 by gamma, that is Rp to the power of gamma minus 1 by gamma, that is equal to 4 to the power of 0.4 divided by 1.4. The T4, the temperature of the gases leaving the turbine, can be calculated as T3 divided by Rp to the power of gamma minus 1 by gamma, that is 1273 divided by 0.4 to the power of 4 to the power of 0.4 divided by 1.4, from which T4 can be calculated in Kelvin. Having calculated the temperatures, we can calculate the work output of cycle as turbine work minus compressor work, that is net work done is equal to Cp of the air into T3 minus T4 minus Cp of the air into T2 minus T1. Because all the temperatures are known, net work done per kg in kilojoules per kg could be obtained. Power output of this cycle is given as 100 kilowatts, that is equal to net work done per kg into mass flow rate of air required, m dot. Therefore, mass flow rate of air required, m dot, that is m over dot, is equal to power divided by net work done per kg, which is earlier calculated. That is 100 divided by work of turbine minus work of compressor in kilojoule per kg. That gives the answer for mass flow rate of air in kg per second. M dot of air is mass flow rate of air required in kg per second. That is the answer for the problem. Now let us solve another problem of gate 99 on gas turbines. The problem is given as an isentropic air turbine, which is nothing but a gas turbine, is used to supply 0.1 kg per second of air at 0.1 meganewton per meter square and at 285 Kelvin to a cabin. Here the cabin means cabin of the aircraft. The turbine is a part of the Bell-Coleman cycle or the reversal Joule cycle meant for the aircraft refrigeration. The pressure at inlet to the turbine is 0.4 meganewton per meter square. Determine the temperature at turbine inlet and power developed by turbine. Assume Cp is equal to 1 kilojoule per kg Kelvin. The solution to this problem can be given like this. Let us draw the expansion of the air in the turbine on a TS plane. The expansion is given as isentropic, therefore the expansion line is vertical line. Both the pressures are given as 0.4 megapascal and the exit pressure is given as 0.1 megapascal. Let us write the isentropic relation between 1 and 2, that is T1 by T2 is equal to P1 by P2 whole power gamma minus 1 by gamma. T1 is not known, T2 is given as 285 Kelvin, therefore T1 by 285 is equal to 0.4 divided by 0.1 whole to the power of 1.4 minus 1 by 1.4. From this, the inlet temperature of the air into the turbine can be calculated. That is, T1 is obtained in Kelvin scale. Having known both the temperatures T1 and T2, the power output of turbine is equal to mass flow rate of air into work done per kg of air. That is equal to mass flow rate of air is given as 0.1 kg per second into work done per kg of air is obtained as Cp of the air into T1 minus T2. Any work output from any gas turbine is calculated as change in enthalpy of the gas, which is nothing but Cp of the gas into change in temperature of the gas across the turbine. Therefore, 0.1 into 1, Cp is given as 1, T1 is given as T1 is calculated in fact, minus T2 is given as 285. So many kilojoule per second or kilowatts. That is how the power is obtained in kilowatts. You can just fill in the blank or rectangle given by, because after substituting T1, whatever is obtained earlier in this formula, we can calculate the power output of the turbine.